So, what if I told you there's a single idea, just one powerful concept that connects the ancient rocks deep beneath our feet to the absolute future of computing? Well, there is. It's called the superposition principle, and the journey this idea takes us on is, well, pretty wild. It all starts with something so simple, so intuitive, you already get it. I mean, think about a massive cliffside, right? Or the Grand Canyon. What you're seeing isn't just rock, it's a history book. Every single layer is a different chapter in our planet's story. And just like any book, there's a basic rule for how to read it. This is where we find the first, most physical version of our big idea, the geological law of superposition. Yeah, a Danish scientist named Nicholas Steno figured this out way back in 1669. It's the absolute bedrock, pun intended, of geology and archaeology. It's how we know that the fossils we find down low are older than the ones we find up high. Simple as that. So at its heart, this first kind of superposition is really just about stacking. You've got these distinct, separate layers, one piled on top of the other in order. Layer 1 goes down, then layer 2, then layer 3. It's just simple, straightforward addition. Okay, but what happens when the layers aren't solid anymore? What if they can actually pass through each other? Well, this takes our simple stacking idea and makes it a whole lot more dynamic. We're moving from solid ground into the world of waves. In physics, this principle gets a bit broader. It applies to any linear system, which is really just a fancy way of saying any system where the effects add up predictably. Think sound waves, water waves, light waves. When two of them meet, their combined effect is just the sum of their individual effects. And this leads to two really cool outcomes. If the peaks of the waves line up, they build on each other, creating a bigger wave. That's constructive interference. But if a peak meets a trough, they cancel each other out, destructive interference. This is literally the magic behind how noise-canceling headphones work. So even with waves, the idea is still pretty easy to grasp, right? Things pass through each other, and their effects just add up. Now, the physics can get super complex. I mean, even a genius like Richard Feynman said it's tricky. But the basic idea is still just addition. And this is where our story takes a hard left turn. We're leaving the familiar world behind and diving headfirst into the strange, almost unbelievable world of the very small. We are now entering the realm of quantum mechanics, where the word superposition means something completely fundamentally different. As Paul Dirac, one of the godfathers of quantum mechanics, pointed out, this isn't just some new twist on an old rule. We are not just adding things together anymore. This is a whole new kind of reality. In his legendary 1958 book, Dirac basically drew a line in the sand. He said this principle isn't just another tool in the toolbox. It is the dividing line. It's the one idea that separates the entire quantum world from everything we thought we knew about physics. It's a revolution. Okay, this is the part that might break your brain a little, so let it sink in. This isn't about adding two separate things, like two waves. This is about one single thing existing as a combination of different possibilities all at once. It's both, and it's neither. Until you look at it. Dirac explains this weirdness using a photon's polarization. So imagine a single photon, a particle of light, passing through a special filter. The theory says that afterward, it's in a superposition of two different states. But here's the kicker. The moment you measure it, it instantly snaps into just one of those states. You always find the whole photon, never just a piece of it. And just look at the exact words Dirac uses here, right from his own text. He doesn't say the photon is one thing or the other. He says it's partly in both states. That language is everything. It's not about adding two things. It's one thing that exists as a hazy, probabilistic mix of possibilities until the act of measuring forces it to kick aside. All right, let's put these two ideas head to head to really hammer this home. This is where it all clicks. So check out this table. On the classical side, it's all about adding separate things. Pretty straightforward. But then you jump over to the quantum side, and it's one thing in multiple states at once. And look at that last row, the outcome. Classically, you measure the total, the sum. Quantally, your measurement forces the system to collapse into just one of its possibilities. It's the difference between a simple sum of parts and a single, weird, probabilistic whole. Here's a great analogy to help with this. Think of classical superposition like 5 guitar strings. The sound you hear is just the sum of 5 individual, separate vibrations. But quantum superposition, especially for entangled particles, is totally different. It's like those 5 particles aren't playing solo. They form one single complex chord. You can't describe one without describing the entire interconnected system. Okay, this is all fascinatingly strange. I get it. But you might be asking, so what? Why does any of this weird quantum stuff actually matter? Well, the answer is that this weirdness is the engine that's going to power our future. Because we can harness this bizarre property, we can create something called a qubit. Now, a normal computer bit is either a 0 or a 1. That's it. But a qubit, thanks to superposition, can be a 0, a 1, or a strange blend of both at the same exact time. And that is the incredible payoff. Because a qubit can explore multiple values at once, a quantum computer can explore an unbelievable number of possibilities in parallel. We're talking about a level of computational power that classical computers could never, ever dream of reaching.
And get this, this isn't just a theory anymore. Scientists have already taken an object, a tiny tuning fork made of 10 trillion atoms, and put it into a state of superposition. It was both vibrating and not vibrating at the very same time. We're actually learning to control this fundamental weirdness of reality. So we started with a simple rule for stocking rocks, and we ended up at the foundation of quantum computing, all by following this one idea. It shows us that deep down, reality is, well, it's probabilistic, it's uncertain. And it really makes you wonder, what other simple rules are just hiding out there, waiting for us to see them in a whole new light?